So the first type of elementary particles are called the fermions. And in terms of quantum physics, that's any particle that has a non-integer spin. Before we actually get into detail on that, a spin is basically a description of the way the particle oscillates in space-time in relationship to itself and other particles. So this is any motion that the particle presents with that's independent of orbiting or spinning around other things. It's basically the oscillation of the particle itself, or how fast it's vibrating in space-time continuum. Because remember that particles can be understood as a wave, or as pure energy that's trapped or anchored to space-time. And this spin can never actually be in chunks which are smaller than half spins. You only have that small of a spin. And it goes back to the idea of quanta, which energy can only, at a certain point when you go smaller and smaller, energy can only be released in small packets. And so since you cannot get smaller than that in terms of energy, the spin cannot be smaller than half. Either you have no spin, which is zero, or you have a negative spin, which if you are antimatter, or you have spins which are actually positive, but starting with halves. So each increment can be a half. Fermions are any particle that have halves of spins, in other words, or multiples of that. For example, a half spin, or a 3/2 of a spin, or a 5/2 of a spin, always a non-integer spin. Those are the fermions. And emerging from this characteristic of having non-integer spins, all fermions have to obey the principle that two particles cannot be in the same spot at the same time. They cannot occupy the same quantum space. And so that means that no matter how much you try to compress these particles, eventually you're going to get to the point where they cannot be compressed any further, and you cannot actually have them ever occupy exactly the same quantum state. Now, the two main kinds of fermions are quarks and leptons. Now, quarks are a little larger than leptons are. They have more energy trapped inside of them than leptons do. And quarks basically are the things that make the most of the matter in the universe. The nucleuses of all atoms are made of up and down quarks organized in different structures to form protons and neutrons. So the up and down quarks, or the first generation flavors of quarks, are going to be the most common types of matter there is. Now, it is possible to get second generation quarks, which are a little bigger, more massive, but their thing is that they're very unstable. It's kind of hard to trap that much energy in one small packet of mass. And so the problem then is that the oscillation will immediately cause the energy to degrade, and the matter will disintegrate and form smaller quarks, such as the up and down quarks. So charm and strange quarks will only show up in specific situations, like inside of stars or in those large particle accelerators that we talked about. But it's been shown that it is possible to create matter that's based on this charged and strange quarks. They're basically particles that don't quite act the same way that up and down quarks act. But it goes back to the whole idea that it depends on how you look at it and when you look at it. And it only lasts a split second. And the very next second you look at it, it's no longer a charming or a strange quark that's there. Now it's an up and down quark. And even more strange would be something like the top and bottom quarks, which have even more mass and therefore even more energy stored in them. Now, do not confuse energy with charge. As you can see, all the up, the charm, and the top quark all have positive charges. And they have 2/3 of a positive charge. So they're not quite one positive charge. They're like a 2/3 of a positive charge. And then a down quark will have 1/3 of a negative charge, and the same thing is true for the strange and bottom quarks. So charm quarks degrade into up quarks, and the same thing is true for top quarks, and strange quarks will degrade into down quarks. The same thing is true for bottom quarks. The same kind of families or generations will be present in leptons. Now, leptons are tiny, microscopic, minuscule constituents of matter, which are not really part of the nucleuses of atoms, and they're basically the vast minority of things of what things are. And they include some particles you may have heard of and some that you may never have heard of before. They include the electron family leptons, which are the negatively charged electron-like particles, and that includes the electron itself, and a little more massive or second generation lepton called the muon particle, and then a little more massive or third generation tau particle. Remember that these strange second and third generation fermions are only noticeable in specific strange conditions, like the inside of stars or large particle accelerators, where matter starts colliding and forming bigger and bigger chunks, or the energy starts being condensed into larger chunks of matter. And then you also have neutrinos, which are even smaller than electrons, and they actually have no charge. That's why we call them neutrinos. And they have electron partners, or in other words, they are kind of like the same electron in their family, like the electron neutrino, or the muon neutrino, or the tau neutrino. Now, electrons and electron neutrinos are the ones which we will see in the case of leptons, just like you will see up and down quarks. Electrons are around in every single atom surrounding the up and down quarks which are forming the nucleus, and the electron neutrinos are the ones which are formed doing those matter-antimatter collisions inside the sun, where the sun actually annihilates matter by colliding with antimatter. 99% of the matter becomes energy, but 1% of the matter is released as an electron neutrino. Muon and tau neutrinos are only present in things like gravitational singularities, gamma rays, cosmic rays, black holes, supernova explosions, and things like that. So these are the fermions, or the most important constituent parts of matter. One interesting fact about fermions is there's a big difference between leptons and quarks, and this biggest difference is that quarks have what's called a residual color charge. And color charge is the equivalent to electromagnetic charges, which you see in the screen here, electric charge. But it's analogous to that, but in terms of the strong interaction, which is a different kind of fundamental force of physics. And we'll talk about that when we talk about bosons in the next video. But remember that quarks, because they have this property, they can never exist by themselves. You never find quarks by themselves. You will always see them in groups of quarks put together, what we call hadrons, and we'll talk about that as well. So I'll see you guys then. In the next video, we're going to be talking about the fundamental forces of physics and how they're mediated by special kinds of particles called bosons or force carriers. I'll see you guys then.